Okay, so we're ready to look at sample problem number 2.6. Now, in this problem, the illustration is right above here, and it says that it is desired to determine the drag force that is at a given speed for a prototype sail boat. So we're looking at like the top view, if you would, of that. So a model is placed in a test channel, and 3 cables are used to align its bow on the channel center line. For the given speed, the tension is 40 pounds in cable AB. So we know what the tension is in this cable. It's 40 pounds. And we also know that it's 60 pounds in this cable. Okay. So they want us to determine the drag force exerted on the hull and the tension in AC. So the drag force is going to be along the horizontal here. And then we're going to have a force along AC. Okay, so we are going to model this so that the center where A is going to be, if you would, our origin on our XY axis. Okay, so what I've done is I already kind of started this in the background. I'll give you a chance to catch up with me. But what I've done is kind of started the sample problem. I put my convention in place, and then I drew my X and Y axis. So I'll be ready to look at the free body diagram. So I'll give you a chance to kind of catch up to this point. Make sure you put your convention up in the upper right-hand corner. And then we'll look at how we generate the forces coming from what would be point A at the origin here of our X and Y axis. We're going to have 4 forces, just so you know. And again, make your illustration or your diagram here nice and big. I'm taking up about half my page, as I normally do. Okay, once you're here, then we're ready to start putting things in place. So first of all, as we look at that illustration, I'll go back and forth this way because I think it's easier to see this. I'm going to start with putting AE in place because we know that that's a force that is 60 pounds and it is going to be pulling away from point A, pointing down. So let's go back here. This is going to be 60 pounds going straight down right here. Okay. And we don't have to give it a variable because it's already got a magnitude. So it's 60 pounds pulling down. Right. We also know that the force going up and to the left here, and it's kind of at an angle right about here. We're going to have to calculate some angles, but I'm just drawing these in place. So proportions are all we're really worried about. This is going to be 40 pounds. This is going to be the force going up to B, from the center A up to B. Okay. Then we've got another force that is going to be, I don't know, something like this from A to C. Don't know the magnitude yet, so we're gonna give this one a variable TAC. And then we do have a 4th force, okay? This is going to be the drag force. So as it said, you're going to notice that here's the flow going this way. This is going to be the drag force. The drag force is going to point to the right. And it's going to be right along the x-axis. And this is going to be FD, the drag force. Okay. Now, in the problem, they didn't give us angles, but we have distances, right? So we have to calculate the angles based on the slopes that were given here. So as you look, the center of the channel is going to be 4 feet from either side. Okay, so that's going to be, if you would, the height of one of these triangles, actually both of the triangles. And then for alpha, we've got a length over here, or one of the legs is going to be 7 feet. So that means that if we want to call this alpha right here, this is going to be the angle right here. So this is going to be what they call alpha. All right. And then as we look there as well, you're going to notice that the other angle is going to be beta from the vertical. So this one is going to be beta. So go ahead and calculate alpha and beta. See what you come up with. Make sure we get the same numbers. I'm going to give you a chance to do that. You get 60.3 for alpha and 20.6 for beta. Okay. All right. And I'll pull the chat box out just to be sure. Okay. If you have any questions, feel free to stick it in the chat box, or my speakers are working here too. All right. So with that now, then we need to, step number 3 is going to be our components, right? Components. Okay. So for TAC and the 40-pound force, we're going to show the X and Y components on our X and Y axis. So I'm going to show those first, and then we'll calculate their values. Like that. And then so that was that B, right? So this will be TABX. Make sure you call the X and Y components of that 40-pound force something. I'm going to call it TABX and Y because it goes from A to B. So the two forces that we need to find X and Y components for are going to be TAC and that 40-pound force. So the 40-pound force will have actual magnitudes. TAC, the X and Y's are going to be in terms of TAC because that'll be an unknown. So go ahead and calculate your components down below. And make sure you add your units in all phases. And I use the pound symbol, very often, or you can use LB if you want to. feel free to take a peek up here to see if your answers, match mine as we move on. So for the TABX and TABY, those have a hypotenuse of 40 pounds. So we can get actual magnitudes for those. But for TACX and TACY, they're in terms of TAC because that's an unknown quantity. So I put the decimal equivalent of the sine and the cosine of each one of those angles. Okay. So any questions so far? All right. So once we have our components, we have everything on the X and Y axis, our next step will be using the equations of equilibrium to see if we can solve for anything, okay? So I'm going to go to my next page, and we are going to use our equations of equilibrium, and we're going to look at the diagram that we created, okay? So number am I on here? Number 4. This is going to be equations of equilibrium. Again, the condition of equilibrium just says that static equilibrium, all of the sum of our forces is going to be equal to 0. There's nothing left over. So we're going to sum forces. Again, by habit, I always sum the forces in the X and then do the Y. So if I'm summing my forces in the Y, you're going to tell me that you're going to do that. So sum symbol, capital F sub X is equal to 0. Okay. So now I'm going to look just on my X-axis, and I'm going to write and give signs to the values that I have just on the X-axis. So you're going to notice that I have a negative TABX, a positive TACX, and a positive FD, which is that drag force. Okay. So I've got a negative TABX, a positive TACX, and a positive FD equal to 0. Make sure you set these equal to 0 because you're summing the forces in the X direction on the left-hand side of the equation and then setting it equal to 0 on the right-hand side. And now substituting these values. So my TABX is a negative 34.75 pounds units plus TACX is 0.3518 TAC plus FD is equal to 0. I'm going to put my negative on the other side. So 0.3518 TAC plus FD is equal to 34.75 pounds. And that's really as far as we can go. So I'm going to put my little cloud around here. Kind of see if our next equation gets us any further. So the other equation we have for equilibrium, I'm going to leave a little space here, okay, because I have a feeling we might come back to this one. So I'm going to leave a little space here so I can go back to it when I need to. And I'm going to start sum of the forces in the Y equals 0 down here. Okay. So now I'm going to bring back my illustration and I'm going to identify the forces on the Y-axis. Things that are going up are going to be positive, down is going to be negative. So in this case, I've got a positive TACY, positive TABY, and a negative 60 pounds. And I'm going to set that equal to 0. Again, everything on the left-hand side has to be set to 0 because we've got equilibrium. Don't forget the equal to 0 here. A lot of students will stop here and then they'll go and then they'll kind of randomly add the equal sign in, and it's risky. All right, and then we'll substitute our values from the components that we got. So TACY was 0.9361 TAC plus 19.82 pounds minus 60 pounds is equal to 0. So it looks like I can combine these two here, right? So I've got 19.82 Subtract 60. So this is negative 40.18. I'm going to move that right to the other side right away. So then it becomes a positive 40.18 pounds, right? So I combine these two over here. It was a negative 40.18. I went to the other side with it and made it positive over here. So then I've got 0.361 TAC. That means that TAC is my only unknown here, right? Cool. Good. I don't even have to do any of that substitution business. So I can divide both sides by 0.9361. So my TAC should be 42.9 pounds. And it's along that line at that angle beta. Okay. So the angle or the direction is identified in our illustration. Okay. So this is one of the unknowns. We wanted to find all the tensions in the cable. So this was the unknown tension, TAC. But now we also have to find that drag force, right? So now that we know TAC, we can go back up here. And this is why we left a little space. We can take our 42.9 and substitute it in here for TAC. And that's what we're going to do. So we're going to say 0.3518 times 42.9 pounds. Make sure you put your units in. Plus FD, our drag force, is equal to 34.75 pounds. Can multiply these out. Our only unknown is FD, so we can solve for that. So 0.35. So that's going to be 15. Go over here. So it's going to be 34.75 pounds minus 15.09 pounds is equal to FD. So FD should be 19.66. Yeah, that's they're fun. I think they are. All right. So for this problem, just kind of reviewing our process, started out by drawing our free body diagram. The center was going to be that center point A, where everything came together. We calculated our angles based on the distances in the diagram where we needed them. We added our components, solved for our components, and then used our equations of equilibrium to solve for those two unknowns, TAC and FD, or FD. All right. Okay, so that's our last sample problem that I was planning on doing this evening. Yeah, of course I can. But what I'm going to do here is I'm going to stop this and then we'll look at the homework.